Imagine you take a box, a strong steel box. You attach a pump to it and you suck out every single air particle. You create a perfect vacuum. Then you shield it with lead so no light, no radio waves, no Wi-Fi can get inside. Finally, you cool it down to absolute zero so there is no heat radiation, nothing. You have a box containing absolutely nothing, right? Wrong. If you look closely at that nothing, you will find it is seething with activity. Particles are popping in and out of existence. Fields are vibrating. Energy is fluctuating wildly. Space is never empty. But here is the catch. When physicists try to calculate how much energy is actually in that empty space, our math breaks. We don't just get it wrong. We get it wrong by a factor of 1 followed by 120 zeros. It is the largest error in the history of science. In this video, I'm going to show you why nothing is actually the most dangerous substance in the universe. We are going to look at the vacuum catastrophe, explain why empty space exerts physical pressure on metal plates, and reveal why, according to our best equations, the universe should have collapsed into a black hole the instant it was born. We used to think of space as a stage, a passive, empty container. The stars, the planets, and the atoms were the actors performing the play. If you removed the actors, you would be left with an empty stage. Silence, stillness. But quantum mechanics tells us this picture is fundamentally wrong. The stage is made of wood, glue, and nails, and it is alive. Even in the deepest void between galaxies, where there is not a single atom for millions of miles, the stage itself is vibrating. We call this the quantum vacuum. But don't let the word vacuum fool you. In our ordinary language, a vacuum means empty. In physics, a vacuum means the state of lowest possible energy. And here's the surprise. The lowest possible energy is not zero. Slow motion footage of a boiling pot of water, but the water is invisible distortion only. If you empty space of all matter, what remains are the quantum fields. We've talked about these before. The electron field, the electromagnetic field, the quark field. They permeate every inch of the universe. You cannot remove them. You cannot turn them off. And because they are quantum objects, they cannot sit still. They jitter. They fluctuate. They are a boiling soup of potential reality. Why? Why can't the universe just be quiet? It comes down to Werner Heisenberg and his famous uncertainty principle. Usually we explain this with particles. You can't know a particle's position and its momentum at the same time. If you pin down the position, the momentum goes wild. But this rule applies to fields too. For a field, position is the strength of the field, and momentum is how fast that strength is changing. If space were truly empty, if the field value was exactly zero, and it was staying exactly zero, you would know both its position and its momentum perfectly. Heisenberg says, no, nature forbids perfect certainty. Think of a pendulum. If you remove all the energy, it hangs straight down perfectly still. That is zero energy. But in the quantum world, that pendulum is never allowed to stop completely. It must have a tiny residual jitter, a zero-point motion, because if it stopped, you would know exactly where it was and exactly how fast it was moving. So the fields that make up our universe are constantly shimmering, even at absolute zero. Look at this. If you are old enough to remember analog television, you know this channel. Channel 0, static. You think this is just a broken TV. But about 1% of that dancing snow is actually the cosmic microwave background radiation, the afterglow of the Big Bang interacting with the antenna. But imagine if your eyes were sensitive enough to see the quantum vacuum. The air in front of you wouldn't look clear. It would look like a blizzard. It would look like a rave. Energy borrowing from the future and paying it back in the past trillions of times a second. We are walking through a dense medium, not a void. So what is actually happening in that blizzard? This is where we meet virtual particles. Einstein told us that energy equals mass. Mass and energy are the same currency, because the vacuum has this jittering energy occasionally that energy spikes high enough to spontaneously create a particle and its antiparticle. An electron and a positron pop out of nothing. They exist for a split second. Then they crash back into each other, annihilate, and turn back into energy. They are like phantom loops. They borrow energy from the vacuum bank, exist for a fleeting moment, and pay the loan back before the universe notices the accounting error. You might think, okay, that's a nice mathematical story, but is it real? Yes, we know it's real because it changes how atoms behave. Inside a hydrogen atom, the virtual photons popping in and out of the vacuum actually nudge the electrons slightly. We can measure that nudge. It's called the Lamb shift. The calculations match the experiments to 10 decimal places. The ghosts are real. But I can give you a proof that is even more physical. I can show you how nothing can push a piece of metal. This is called the Casimir Effect. Imagine two uncharged metal plates. You place them incredibly close together, micrometers apart. There is no electrical charge, no magnetism, no gravity. They should just float there, but they don't. They get pushed together. Why? Think of the vacuum fluctuations as waves. There are big waves and small waves. Outside the plates in the open universe, all sizes of waves can exist. Big rolling swells and tiny ripples. But between the plates, the space is tight. The big waves don't fit. They are excluded. Only the tiny ripples can fit in the gap. This creates a pressure difference. Outside, lots of waves pushing in. Inside, very few waves pushing out. Result, the nothing outside is stronger than the nothing inside. The plates are crushed together by the sheer weight of empty space. We have measured this in the lab. It is a fact. The vacuum has pressure. Now, every time I explain this, someone asks, wait, if space is full of energy, can we build a machine to suck it out? Infinite free power? The answer is no. Remember the beach towel analogy? Energy is only useful if there is a difference. If you are wet and the towel is wet, you can't get dry. We live in the vacuum. We are at the same potential as the vacuum. To extract energy from it, you would need a region of less than nothing to flow into. And as far as we know, you can't go lower than the vacuum state. It's like trying to drink the ocean while you are swimming underwater. The water is there, but you can't make it turn a turbine because there is nowhere for it to fall. So we know the vacuum energy is real. We can measure it pushing plates. We can measure it nudging electrons. Now comes the embarrassing part, the calculation. Physicists thought, okay, let's calculate exactly how much energy is in a cubic meter of empty space. To do this, you just sum up the energy of all the waves. You take the energy of the long waves, plus the medium waves, plus the short waves, plus the tiny waves. But remember, space is continuous. The waves can get smaller and smaller and smaller. As the wavelength gets shorter, the frequency gets higher. And Einstein showed us that energy equals frequency. So as the waves get tinier, their energy gets massive. If you keep adding them up all the way down to the smallest possible size, you don't get a small number. You get a number that is effectively infinite. The calculation says that the empty space inside your coffee cup contains enough energy to boil all the oceans on Earth instantly. In fact, it says a cubic centimeter of vacuum contains more mass energy than the entire observable universe. This is called the ultraviolet catastrophe of the vacuum. So what, you say? It's just a number. Maybe the energy is there and we just don't notice it because it's uniform. That was the hope. Maybe we are just fish swimming in very heavy water and we don't feel the weight. But there is one thing that does feel the weight, one thing that cannot ignore energy: gravity. General relativity tells us that gravity is caused by mass and energy. Energy curves space-time. If empty space really had that much energy, 1096 kilojoules per cubic meter space would be curved so tightly that the universe would instantly curl up into a ball. The universe should not be large. It should be the size of a grapefruit. It should have collapsed into a singularity moments after the Big Bang. But look around. The universe is huge. It is billions of light years wide. It is expanding. This means the vacuum energy cannot be huge. It must be tiny. So here is the mismatch. Theory says the vacuum energy should be huge, a number with 120 zeros. Observation says the vacuum energy is tiny, a zero, a decimal point, 120 zeros, and then a 1. This is a discrepancy of 120 orders of magnitude. Imagine you asked me to estimate the size of the entire observable universe, and I told you it was smaller than a single atom. That is how wrong this calculation is. This is the cosmological constant problem. If we trust our quantum math, the same math that gave us the laser, the transistor, and the MRI space should be heavy. If we trust our gravity math, the same math that predicts orbits and black holes, space must be light. Both theories work perfectly on their own. But when you put them together to ask this one simple question, how much does nothing weigh? They scream at each other. This is the biggest crisis in modern physics. It tells us that something is fundamentally broken in our understanding of reality. Maybe gravity leaks into other dimensions. Maybe there is a hidden symmetry that cancels out the energy. Or maybe our concept of space itself is an illusion. But the next time you look at an empty box or look up at the dark night sky, don't be fooled. It isn't empty. It is a roaring ocean of energy, balanced on a knife edge, hiding a secret that we haven't solved yet. If you want to understand the dark energy that is actually stretching the universe apart right now, hit subscribe. We are going to dive into the death of the universe next. And if this broke your brain a little bit, I've created a quantum weirdness cheat sheet. It breaks down virtual particles, the Casimir Effect, and the Vacuum Catastrophe into simple diagrams you can actually understand. Click the link below to download it for free.